right, recap of the lab that we did. We actually had a lacrosse ball, and the mass of the lacrosse ball was 14.15 grams. That needs to be converted to kilograms. So that's going to be 0.01415 kilograms. I'm going to keep, I have 4 sig figs here. What you did, you allowed that lacrosse ball to fall from something under 1 meter. Some of you chose 1 meter. My caution is if you write this, you only cut yourself to 1 sig fig. So we can do 1.0 meter, or let's say it fell from 95 centimeters. Now stick to your own numbers. This is just hypothetical. Let's say I allowed it to fall from this 0.95 meters and it bounced back to 0.65 meters, a bouncy ball right there. It bounces back up with a lower height because some of the energy is transferred into internal energy, into energy of sound, because we heard that bump. Calculate the work done by force of gravity on the way down. A lot of you got a little bit mixed up. This is not part of it yet. It just fell this distance. So work of gravity, as per usual, is going to be found as force of gravity times displacement. And in this case, because they were both downwards, it's going to be cosine of 0 degrees. So 0.01415 times 9.8, that's 2 sig figs now, times 0.95. Again, I'm using my numbers, you use your numbers, thank you. The work done by gravity would be 0.13 joules. Now, calculate the ball's change in potential energy during the fall. At the top, potential energy initial is going to be mgh, where h is 0.95. It's going to be the same. It's going to be 0.13 joules at the top. Potential energy gravitational final is going to be 0 because it's going to be on the ground, which ground, or if you use the desk, could be, this is your 0 level. This is where potential gravitational energy is 0. So then 0 minus 0.13 joules gets me negative 0.13 joules. That's the change. Negative 0.13 joules. And then what do you see? You see that gravity does positive work, but that leads to the loss of potential gravitational energy. So right here, I'm going to put equals negative. Then consider air resistance negligible and use conservation of mechanical energy. Mechanical energy includes potential energy gravitational, potential energy elastic, which you do not know yet. It connects with the springs. We're going to look at it later. And kinetic energy that we started with. So these two guys you know already. So in the beginning, the ball had potential gravitational energy. It wasn't moving, so it didn't have kinetic energy. At the end, it's on the ground, so it no longer has gravitational energy because I assigned 0 level to the ground, but it is moving. Right before it hits the floor, it has a certain velocity. So to figure out velocity, what we continue to do is we cancel the mass, then multiply by 2, and we get 2 gh initial equals to square of v final, from where v final is going to be a root of 2 gh initial. Then make sure you're showing all of this on your lab report to get full credit. If you don't, well, you only have yourself to blame. 2 times 9.8 times 0.95, because I assigned my initial height to 95 centimeters. That gets me 4.3 meters per second. This is how fast the lacrosse ball is moving if I dropped it from 95 centimeters and disregard air drag. On the way back, I assigned my final height to go back up to 65 centimeters. So again, potential energy at the bottom is 0 and it's initial. It has kinetic energy initial, which I do not know, but I know that in the end, when it bounces back up to 0.65 meters, it has potential energy gravitational final equal to mgh final. The work of gravity on the way back up is going to be opposite to the change of potential energy. And my ball gains potential energy because it goes above the floor. So final potential energy minus initial potential energy, gravitational potential energy in the beginning is 0. In the finale, it's going to be 0.01415 times 9.8 times 0.65 0.09. It gains 0.090 joules of energy. And that 0.090 joules of energy means that gravity did negative 0.090 joules of work. Why is that? Because gravity is downward, displacement is upward. They were opposite each other. There was a cosine of 180, but you also know that because you established this in the beginning. Derive this. Kinetic energy initial is going to be equal to potential energy gravitational final, mv initial squared divided by 2 will be equal to mgh final. Mass cancels. V initial is going to be root of 2gh final. And in my case, it's going to be a root of 2 times 9.8 times 0.65, 3.6 meters per second right before. So it fell with 4.3 meters per second and bounced back with 3.6. Some of the energy was not, air quotes, lost. It was transferred into internal energy and the energy of sound. Alrighty. Now, we're going to practice. We start with a diver 10 meters above the water. So we have potential gravitational energy due to him being above the zero level. So this is my zero level where potential energy gravitational final equals a 0. Boom, boom. I need to figure out kinetic energy final here at this. So I had potential energy gravitational initial, which was equal to mgh. The diver had a mass. I don't know what that mass is, but I don't need it because I'm going to say mechanical energy is conserved. It's constant. So I have potential energy gravitational initial should be equal to kinetic energy final. And then mgh initial is going to be equal to mv final squared over 2. Kindly work this out. Do not jump to the final formula. You have to practice it because it's going to get a little more complicated when we throw in the energy of springs. So that gets me to V final being root of 2gh initials. So then V final is going to be root of 2 times 9.8 times 10, 14 exactly meters per second. Now, find the speed when he's halfway, 5 meters above water. So that tells me that he still has potential energy in the end. So we are right here. So it has potential energy gravitational final plus kinetic energy final. And I'm going to write this out as mgh initial equals mgh final plus mv final squared over 2. Mass cancels as before. Then I can do g, h initial minus h final. So that's going to be 10 minus 5. So it only falls 5 meters equals v final squared over 2. So then it's going to be just v final is going to be a root of 2 times g, which is 9.8, and times 5. So it's going to be a little less than that. Not half though. That's the interesting part. It's going to be 9.9 meters per second. So if you have a root of 2 kinetic energies over mass, this is now half of it. So you basically are dividing by a root of 2. Let me check. 14 divided by a root of 2. What do you know? 9.9. That is for later. Another diver jumps. This should be off the same diving board with 5 meters per second. Then what we have is in the beginning, he has potential energy gravitational and kinetic energy initial. And in the end, potential energy gravitational 0, he just has kinetic energy final. So that's how we're going to write it out. Potential energy initial from gravity plus kinetic energy initial because he jumped equals to kinetic energy final. mgh initial plus mv squared initial over 2 equals mv final squared over 2. Cancel masses. Multiply by 2, so I have 2gh initial plus v initial squared equals V final squared. Look at that. We've seen this formula before. Remember, we had the formula V final squared equals V initial squared plus 2 acceleration and displacement. This was a very old formula, but now you understand where it came from. Please, please, please do not jump to that formula, because if you jump to that formula, you tell me that you have learned nothing since then, and that is not true. So V final is going to be a root of 5 squared, which is 25, plus 2 times 9.8 times 10 if that person jumped from the height of 10. So 25 plus 19.6 times 10, 14.9 meters per second. So slightly faster than just 14 because he had initial kinetic energy. If instead of upward, he jumps downward, that technically means the V initial is negative 5. But when you do mv squared over 2, that's still the same because negative 5 squared is the same as 5 squared. So it does not matter. And it does not change because kinetic energy has no direction. It's always positive. So it doesn't matter how you jump. You have that energy regardless of your direction of motion. Energy doesn't have direction. So therefore, it will have the same energy whichever way you jump. And that energy will translate into your final kinetic energy. Again, no matter how you jump, you still have that energy. So the answer doesn't change.